Hello everyone, welcome back to my channel. In our today's video, we will be continuing with the p block elements, and we will be learning about the final group of the p block, that is group 18 elements. As we know that this group 18 elements are also called noble gases, or in some of the reference books and some of the textbooks we get it as inert gases also. There are 6 noble gases. They are helium, argon, neon, krypton, xenon, and radon. These are the 6 noble gases which we have. So in our today's video, what we'll be going to do is we'll be learning about this particular elements, their electronic configuration, and why they are called noble gases, why they are inert, why they are so less reactive. And we'll try to find out also that if there is any noble gases which will be reacting and which will be forming compound, which one it is and why it is so, and what type of chemical reaction it undergoes and what type of compound it forms. So let us go on with the introduction of the group 18 elements. The group 18 element, also known as group 0, remember that, of the periodic table consists of 6 monoatomic gases. Okay, they don't exist as molecular form, they exist in atomic form, and that is nothing but helium, neon, argon, krypton, xenon, and radon. Okay, except radon, remember that all other gases are present in our atmosphere. Okay, radon is not present in our atmosphere. Other than that, all are present in very small quantities, but they are naturally present in our atmosphere, and hence they are also known as rare gases of atmosphere. Okay, and remember that radon is a radioactive element. Okay, so radon in this particular series of elements, in this group of elements, radon is the radioactive element. Okay, these gases are collectively called noble gases, as I have already told you. Now the question is why they are called noble gases. Okay, they are also known as inert gases, but noble gas is a correct name for them instead of inert gas. Okay, before we used to call them inert gases because they had no reactivity. It was found out that they don't react with any other chemical substance. Later on, it was found out that some of the noble gas, they do react. It's just like a property of noble metals like gold and platinum. They have very low reactivity. That does not mean they don't react. Okay, the reactivity is very, very low, no doubt, but they do undergo chemical reaction. They do form some compounds also, and that is why we call them noble gases. Has a very less affinity for going into chemical changes or chemical reaction. Okay, now coming for the electronic configuration of these elements, as they are noble gases, we always have discussed this, and we always know that. Okay, we have learned from our elementary classes that noble gas has a fully filled configuration. So this are stable. Okay, one of the major reason of noble gas being so stable and unreactive is because of their fully filled configuration, which you can clearly see in this configuration. Like helium is 1s2, neon is helium 2s2 2p6. Okay, argon is neon 3s2 3p6. Neon stands for 1s2 2s2 2p6. Okay, and 3s2 3p6 is the outer shell configuration. Then krypton, if you can see, 4s2 4p6. Xenon, it will go for 5s2 5p6, and radon, it will go for 6s2 6p6. So what you can see in this particular elements is these elements have fully filled configuration. Their last shell is completely filled, as a result of which they will have very, very less tendency to go for any gain or loss of electron. They don't want to lose because they will lose their stability. They don't want to gain because they are already stable. By gaining electron, they actually become unstable. So they want to remain in that atomic state only. That's why they exist as monoatomic gases. Okay, so if you see their last configuration, okay, except helium, okay, if you see from neon to radon, their general configuration can be written as ns2 np6. Okay, now coming for the next, now the most important question, as I was discussing, that why are noble gas inert? What makes noble gas inert? Okay, Why they are not reactive? As I've already told you, one of the reason is because of its electronic configuration. They have very, very stable electronic configuration. They have fully filled configuration. Because of this fully filled configuration, they have very, very less tendency to react. Okay, why they will react? Because they are, see, any system is reacting because either they have less electron in their system, okay, and because of that they are not stable, so they want to go for that fully filled configuration. So because of which they either gain, lose, or either they will actually go for sharing of electrons. So that depends upon the system. Over here it is completely filled, so it will never have a tendency to go for the bond formation, to gain electron or to lose electron or to share electron. Second one, they will have very high ionization energy. As we know that when we move from left to right, the ionization energy goes on increasing. Group 18 elements or this noble gases are the extreme right. Okay, so they will have very, very high ionization energy. The energy required to remove their valence electron will be very, very high. As a result, it becomes very difficult for them to participate in electron. Not only that, they will have very, very low electron affinity. They will have no tendency to take electron. They have positive electron gain enthalpy. Remember that. Okay. As a result, no tendency to gain, no tendency to lose. As a result, they will never take part in bonding. That is what actually it was found earlier. Okay. But it was found out that the xenon do form actually chemical compounds. Okay. So it was actually not in the early what do you call it, in the early discovery, when the noble gases were discovered, this particular systems were found to be very much unreactive. So they thought that this particular reaction or this particular noble gases will never react. Many attempts were done, okay, but it was found out that they will not react, okay, or they are not reacting. In 1962, Neil Bartlett, okay, then actually the University of British Columbia, okay, observed that noble gases actually do react. Okay, he found out that the enthalpy of a molecular oxygen, okay, the ionization enthalpy of a molecular oxygen was almost identical with xenon. Okay, so when he found out that the ionization enthalpy of molecular oxygen is almost identical to that of the xenon. Molecular oxygen has ionization enthalpy of nearly 1175 kilojoule per mole, okay, whereas xenon has 11770 kilojoule per mole. That means it is possible to take out electron from actually xenon. Then he actually made some reaction, made some preparation, and he finally prepared a compound of xenon, that is XePtF6, platinum complex of xenon, where xenon is existing as Xe plus and PtF6 minus. Okay, it was the complex of platinum which was first made by Neil Bartlett, okay, and Bartlett, sorry. And what he found out is that by mixing platinum fluoride, PtF6 and xenon, he could get, or it could be actually xenon complex can be easily prepared. Okay, then after that discovery, okay, after the discovery of that particular complex, then many actually complex of many compounds of xenon was prepared, okay, particularly reacting it with the electronegative element. It was found out that xenon will prefer to react with oxygen and fluorine. Why? We'll try to come into this particular topic. But now the question is, okay, xenon reacts, we found out that, but now why xenon? Why not other elements? It was found out that if you see the group of this particular noble gases, xenon is the last element. If we don't take radon, since it is radioactive, so if I take xenon, which is the last element of this particular group, see, being the last element, obviously it will have the biggest size and have the lowest ionization enthalpy. Whenever you move down the group, ionization enthalpy decreases. Having the lowest ionization enthalpy make it possible for it to lose electron. As a result, it reacts to form chemical compounds. That was the reason. It is because of the lowest ionization energy of xenon. Now the next question is, okay, xenon reacts, but why only with fluorine and oxygen? So why noble gas form compounds with oxygen and fluorine only? Why not others? When it was actually studied, obviously we know that oxygen and fluorine are the most electronegative element. They have a huge tendency to gain electron. They have a very, very high electron affinity. As a result, they are very powerful oxidizing agent. They can make xenon lose electron easily. As a result, fluorine and oxygen, since being the most electronegative element, will be very reactive and will be powerful oxidizing agent. Hence, they can easily form compounds with noble gas, particularly with xenon. And why xenon? We have already discussed that, because of low electroionization enthalpy of xenon. Okay. Now, after understanding that, okay, xenon do react and form chemical compound. Now, the next question is, what are the compounds of xenon? Okay. Now, as we have just now studied that xenon reacts with fluorine and oxygen. So it forms usually two kinds of compounds, that is oxides and fluorides. But we have other actually kind of complexes of xenon, that is xenon oxyfluorides also. Okay. So fluorides, okay, the first actually fluorides of xenon, okay, which we can see in the screen is xenon when it reacts with fluorine, okay, in nickel tube. Obviously both are gases, xenon and fluorine. So when you react actually xenon and fluorine in the ratio of 1:2 in nickel tube and heat it to 673 Kelvin, what it forms is xenon difluoride, okay, XeF2. The same xenon, when you react with fluorine in the ratio of 1:5 in nickel tube at 673 Kelvin by applying a pressure of 5 to 6 atmosphere, then it will form XeF6, xenon tetrafluoride, okay. The same xenon, when it reacts with the fluorine in the ratio of 1:20 in the nickel tube at 575 Kelvin, nearly to 50 to 60 atmosphere pressure, then what was found out that we get xenon hexafluoride. So the ratio in which we are taking them will be very, very important. Okay, the 1:2 ratio, 1:5 ratio, and 1:20 ratio actually decides the formation and their condition. Okay, in some cases we have to apply less pressure, in some of the cases we apply very high pressure. Okay. Now, coming for the next compound of xenon, that is oxides and oxyfluorides. Okay, as I have told you that it reacts with oxygen and fluorine. So oxides and oxyfluorides, we usually get it from the fluorides, okay, by hydrolysis. Depending upon the extent of hydrolysis, whether we'll do a complete hydrolysis or whether do we actually do the partial hydrolysis, depending upon that, sometimes we get oxide, sometimes we get oxyfluoride, sometimes we get xenon also. Like for the very first one, you can see over there, XeF2 is hydrolyzed completely by water. Okay, whenever you react XeF2 with water, what you get is XeO2 and HF. Okay, so XeF2, whenever you hydrolyze with water, what it gives you is xenon, oxygen, and hydrogen fluoride. When you take XeF4 and react with water to actually react with water, it again goes complete hydrolysis but gives you a highly explosive solid, and that explosive solid is nothing but xenon trioxide. It's an oxide of xenon. How do you get it? XeF4, when it reacts with water, complete hydrolysis, complete removal of the fluorine by oxygen, as a result of which what we'll get is xenon trioxide, HF, and oxygen. Okay. When you go for partial hydrolysis of XeOF2, okay, so when you go for partial hydrolysis, what it will yield is XeOF2. Partial hydrolysis basically will not be removing all the fluoride of xenon fluoride, will be removing few and few will be left. Like in XeF2, when you react with water, what will happen is one of the oxygen will replace two of the fluoride. As a result, what you get is XeOF2 and you get 2HF. So oxygen also and fluoride also. That is what we call as oxyfluorides. Okay. Partial hydrolysis of XeF6 yields XeOF4. Okay. Whenever you take XeF6 and do partial hydrolysis, it will give you XeOF4. Okay. And the same thing when you do complete hydrolysis, it will give you XeO3, which actually you can see on this screen. XeF6. This is partial hydrolysis. We are just removing two fluorine by an oxygen. So what you get is XeOF4. The same thing when XeF6 reacts with, see, 3 molecules of water, completely all the fluoride will be removed by oxygen. So you get XeO3, that is xenon trioxide, and 6HF. So it depends upon the extent of hydrolysis. Okay, what do you actually do, how much extent you are hydrolyzing, depending upon that you get different kinds of oxides and oxyfluorides of xenon. Okay, coming for the next, xenon trioxide is prepared by complete hydrolysis, as I have already told you. by hydrolysis of XeF4 and XeF6, which we have done. Okay, so whenever you react xenon trioxide, if you want to prepare xenon trioxide, if you react XeF4 and XeF6 and do complete hydrolysis, remove all the fluoride with oxygen, then you get xenon trioxide in both the cases. So that is how we prepare oxides and oxyfluorides of xenon. Okay, this will be very important. So remember that the oxides and oxyfluorides of xenon is prepared from fluorides of xenon. Okay, so when you have XeF2, XeF6 and XeF4, from there you can easily prepare the oxides and the oxyfluoride, depending upon how much is the extent of hydrolysis. Now, finally, coming for the structure of xenon compounds. Okay, so I have taken few structures of xenon compound, like XeF2 will be linear, but remember that its geometry will be trigonal bipyramidal, having 3 lone pairs. So obviously it goes for linear structure. XeF4 will be square planar. Okay, but its geometry will be octahedral since it has 2 lone pairs, so it goes for square planar. XeF6 will be distorted octahedral. It has 6 bonds, but remember that 1 lone pair also, so it goes for distorted octahedral. This lone pair actually repels the other bond pair, and the angle will not be 90 degree as in case of octahedral. So that is why we call it distorted octahedral. Then we have XeOF4. Okay, that is the oxyfluoride of xenon. It will have a geometry of octahedral, no doubt, but one of them is lone pair. As a result, it will go for square. The 4 fluorine forms a square. Connecting with oxygen gives you a pyramidal. That is what we call a square pyramidal. And finally, coming for XeO3, it is tetrahedral geometry, but one of them is lone pair. As a result, it will go for XeO3, that is xenon trioxide. And the structure which it goes, or the shape, sorry, which it actually takes is nothing but pyramidal. When you connect this 3 oxygen, what you get is a pyramidal. Okay, so that is how actually we can understand the geometry or the shapes of various xenon compounds. So that is all about the noble gases. Okay, so that is what actually we have to know about noble gases. Okay, so noble gases are very inert. Why they are inert? Why xenon is the compound which reacts, or why xenon forms compounds, why not the other noble gases? Then why xenon forms compounds with fluorine and oxygen only? Then what are the different fluorides of xenon? How the fluorides can be converted to oxides and oxyfluoride? What is partial hydrolysis and what is the complete hydrolysis of xenon and their particular reactions? These are the limited reactions of xenon which we have studied till date, and the structure finally of xenon compounds. Okay, so with that we are done from the noble gases, okay, and its various properties. So thank you everyone. Do subscribe for this channel for explanation on various topics in chemistry. Thank you.